Adjunct Professor Moran, Microeconomics, and we're going to start off by discussing the optimal amount of pollution cleanup. Get that? The optimal amount. So we're going to use cost-benefit analysis to decide how much pollution to clean up. The human environmental damage caused by industrial pollution often arouses public attention. While it might be nice to restore our environment to its pristine state, pollution cleanup is costly, and dollars used for cleanup might be spent elsewhere. In other words, there's an opportunity cost for the money that you could spend on pollution cleanup that after a certain point, as the benefits of cleaning up the additional amounts of pollution, that the benefits get less, and you might be better off spending the money doing something else with that money. It seems then that some sort of balance must be struck between undesirable pollution and costly cleanup. Let's apply marginal analysis to determine the optimal amount of pollution cleanup. The marginal social benefit of cleaning up pollution tends to decline as additional units are cleaned up. The marginal and social cost of cleaning up pollution tends to increase as additional units of pollution are cleaned up. If society has an accurate information about the total social benefits and costs of various amounts of cleanup, society should then be able to get as close as possible to the most efficient optimal level of cleanup, where marginal benefits equal marginal social costs. There was a company called Hooker Chemical, and they built their factory in an area called Love Canal, upstate New York, near Niagara Falls. Originally, at the turn of the 20th century, it was supposed to be an ideal community. But it was never fully developed, and so eventually Hooker Chemical opens a factory there. And they're generating a lot of waste. Now, to minimize costs, they decided they were going to bury the wastes in the area. So they're burying all of these wastes in the area. And naturally, they start leaking out. And then there was a baby boom, and the local community wanted this area to build housing and schools on. And Hooker Chemical said, no, we don't really think that's a good idea. And so the local government threatened the use of eminent domain to take the property away from Hooker Chemical. So Hooker Chemical sold it to the local community for $1 with the reservation in the contract that Hooker can never be sued for anything bad that happens. So naturally the drums start leaking, and people get terribly ill. It's a real tragedy. It made a lot of news, I believe, in the late 60s, early 70s. You know, imagine your home, everything you own is locked up on an area with serious amounts of pollution, causing lots of bad effects. Something similar happened out on the West Coast with Pacific Electric and Gas, and that's what the movie Erin Brockovich is about. And Julia Roberts plays Erin Brockovich. Woo woo. So you would want to check that out. That's an interesting movie. Anyway, when it comes to marginal cleanup, it's relatively cheap to clean up the surface waste. Right? The cost isn't a lot. It's right on the waste, and the benefit is great because it's easy to get contaminated. But to get more pollution costs more money. But that pollution is less likely to make anybody sick, so the benefit is less. So more cost to get more and more remote pollution, so the cost is going up, and the benefit of getting sick, the likelihood of getting sick from more and more remote pollution, for example, is getting less. So this would be your supply curve, which is your marginal cost curve, and this is your demand curve, which is marginal benefit. And you're going to want to find the point at which the marginal cost equals the marginal benefit, and that's what they consider the optimal amount of pollution cleanup. And this is great if you're a lawyer sitting in a boardroom someplace, but if you're the person actually has the house nearby, you might consider a little more rigorous cleanup than an economics book would recommend. But this is economics, so that's what we're going to be doing. We're going to be doing the optimal amount of pollution cleanup by using marginal cost, marginal benefit. Okay, imagine a community in which two firms emit foul sludge. Now, foul sludge is somewhat of an oxymoron, redundant, right? Because is there any really attractive sludge? So they're emitting foul sludge into two local lakes, one for each firm. Natural processes gradually break down the sludge, rendering it harmless. But as long as emissions continue, a certain equilibrium level of harmful sludge remains in the lake. If the emissions are lowered, this equilibrium level will be reduced. The opposite occurs if emissions are increased. Currently, each firm emits 5 units of foul sludge each week. Okay. So you send your scientists out there, and they're measuring the foul sludge. And this is what they discover. This is how much sludge they can clean up. And this is the benefit to society measured in dollars. So believe it or not, economists and insurance companies can measure the value of a human life. It's basically the discounted future earnings value of your income stream over your life. All right, so here's the social benefit. Could be tourist dollars. It could be people not harmed by foul sludge. But we don't make decisions based on totals. We make decisions based on marginals. So we have to calculate our marginal social benefit. Then there's a total cost of cleanup. And you can see that the cost gets more and more expensive. But we don't make decisions based on totals. We make decisions based on marginal. Okay, so let's just calculate our marginal. So again, a marginal comes from two different lines. It's a change measure. When asked for an average, everything comes from one line. It's a snapshot in time. Also keep in mind that when you're doing marginals, it's this number divided by the change in this number divided by the change in this number. But since these numbers are changing by 1, it's easy to overlook the fact that you're actually dividing by the change of 1. 350 minus 0, 650 minus 350, 900 minus 650, 1100 minus 900, 1250 minus 1100. Now we have our marginal social benefit. Notice the marginal social benefit is declining as additional units of foul sludge is cleaned up. Okay. Our marginal social cost, 160 minus 0, 160. 370 minus 160 is 210. 630 minus 370, 260. 940 minus 630 is 310. And 1300 minus 940 is 360. Notice the cost of cleaning up the pollution rises as we continue to clean it up. Okay, the marginal social benefit of reducing emissions by the first unit of foul sludge, the marginal social benefit of the first unit is 350. And the marginal social cost is 160. So here the benefit is exceeding the cost, so we're going to clean up the first unit of foul sludge. The marginal social benefit is greater than the marginal social cost. So it would be economically efficient from society's point of view to require Firm 1 to reduce pollution by the first unit. The marginal social benefit of cleaning up the last unit of foul sludge is 150, and the marginal social cost is 360. The marginal social benefit is less than the marginal social cost, so it would not be economically efficient from society's point of view to clean up the last amount of foul sludge. In fact, the last time that the marginal social benefit exceeds the marginal social cost is here at 2 units, at 300 benefit and 210 cost. So you would stop here because on the third unit, the marginal social benefit is 250, whereas the cost is 260. In this example, you never have an exact equilibrium. So here's 2. The benefit, read from the demand line, the marginal benefit is 300, and the marginal social cost at 2 units is 210. You would not go ahead and do the third unit because the marginal cost is greater than the marginal benefit. I didn't draw this to scale. 2 units, marginal social benefit greater than marginal social cost. You're going up from 2 and comparing at 2 units. You're comparing which line is greater, and the demand line is, the marginal benefit line is higher than the marginal cost line. But if you go to 3 units, then 250 is less than 260, so your benefit is less than your cost, and you would not clean that up. Here's a second factory, also emitting foul sludge into a different lake. 350 minus 0 is 350. It has the same benefit curve. But here at this lake, the costs of cleaning up are different, and it's 160 at every level. Would you clean up the first unit of foul sludge? The benefit is $350. The social cost is $160. Yes. Would you clean up the second one? The benefit is $300. The cost is $160. Yes. Notice we're not using totals. We're seeing, now that we're here, we're going to do the next one. What's the benefit? The marginal benefit of the next one. What's the marginal cost? $250 and $160. $200 and $160. $150 and $160. No. So the optimal amount of cleanup is 4 units of foul sludge. The marginal benefit of eliminating the 4th unit of foul sludge is $200. And the marginal social cost is $160. The marginal social benefit is greater, so it would be economically efficient. But the 5th unit, the benefit of the 5th unit is $150, and the marginal social cost of the last one is $160. The marginal social benefit is less than marginal social cost, so it would not be economically efficient to clean this up. At 4 units of foul sludge cleanup, keep going until you hit both lines. The benefit is $200, the cost is $160. Marginal cost $160, marginal benefit $200. Benefit exceeds the cost, clean up this one. At the 5th unit, the social cost is $160, but the benefit is only $150 at 5 units. So here you do not clean up the 5th unit because the social cost is greater than the social benefit. Using marginal benefit, marginal cost to clean up, decide the optimal amount of pollution cleanup.